Okay, all right. Well, hello, and I hope you guys are doing well. And It seems like, well, at least at my location, we got quite a bit of rain, but we fared well and did okay. And I hope you guys are doing well wherever you guys are. But yeah, and thanks for meeting online. Um, let's continue on. We left off on Wednesday. We introduced neural networks. We did forward propagation, and so let's just kind of do a quick review of what that looks like. Um, in our neural network, we have two variables coming in. Our variables are just labeled hours of sleep and hours of study. And then the network goes through. Basically, those two values come into our function, and then it outputs one value, which is our predicted test score. And right now, our neural network has one hidden layer, and the hidden layer has three nodes. And so we take our input, we're going to multiply it by our first weight matrix, which consists of 6 values arranged in a matrix of 2 rows and 3 columns. And that's going to produce 3 values, which represent the values in our hidden layer, one value at each node. Those values get processed by an activation function. And we take the active values that come out of the activation function, we multiply by another matrix of weights, our second weight matrix. And those combine into one values, and we put them through another activation function, and those become our predicted values. And so our weight matrices look like this, and we have our activation function, which is the logistic or the sigmoid activation function. And the process as far as forward propagation looks kind of like this. We take our X matrix, multiply it by our first weight matrix W, we get Z2, we put that in our activation function, we get A2, we multiply those results by our second weight matrix W2, that gives us Z3, we put those into our activation function, and those are our predicted values. And so this is what we have for forward propagation. And so now we are in the situation of how do we pick the values that go into our first weight matrix, our W1 matrix, and the values that go into our W2 matrix. That's basically what training our model comes down to. It comes down to figuring out what values go into these weight matrices. In your next homework assignment, you will have bias terms, and you'll also have to figure out what values go into the bias matrices. But this is where we are now. And so what we want to do is we want to pick the values in our two weight matrices, our W1 and our W2 weight matrices, so that the resulting Y hats are as close as possible to the actual values Y. Our loss function is going to be basically the mean squared error. We take the difference between the actual value Y and our predicted value Y hat, and we take that difference and we square them, and we basically want to pick the W1s and the W2s so that the Y hats are as close as possible to Y. So this is what we're going to do. This is our loss function. And the way we're going to figure out the values for W1 and W2 is we are going to take the gradient of the loss function with respect to W1, and we're going to take the gradient of the loss function with respect to W2, and we're going to use gradient descent so that we find the values that go into W1 and W2 that will lead to a minimum of the loss function. If we could, we would take the gradient of the loss function with respect to W1 and with respect to W2, we would set those gradients equal to 0, and we would solve for W1 and W2, and that would give us a solution. That would be, basically where the gradient is equal to 0 and the gradient is equal to 0 at either a local minimum or a local maximum, and we'd figure that out. But unfortunately, these equations are too complicated that even if when we find the gradient, it's going to just be a little bit too hard for us to set that equation equal to 0 and solve. So we have the gradient, and what we're going to do is we're going to do gradient descent. We're going to start off at some arbitrary location, and we'll say, keep taking steps downhill. And as we take steps downhill, our loss function will get smaller and smaller and smaller. And eventually we'll reach a point where the loss function doesn't get any better as we take more steps downhill. We're kind of reach maybe like a flat area where the loss function doesn't seem to improve. Okay, but that's what we're going to do. Now, as far as making our derivations work a little bit easier, calculating the loss function, I'm going to modify the loss function. We're going to just multiply the loss function by a constant n over 2, and we will get this 1/2 of this. But basically, the value that optimizes this, the value that minimizes equation J, is going to be the same value that minimizes equation L, because we're just changing W1 and W2, so it really doesn't matter if we're just multiplying the entire thing by a constant. Okay, so this is where we are, and what we want to do is we want to figure out, okay, what is the gradient? Okay, what is the gradient of our loss function with respect to W1 and W2? So we have two gradients to figure out. And that's basically what backpropagation is. And we're going to do backpropagation kind of from this vector calculus method, vector calculus perspective. And we're going to say, okay, what is the gradient of our loss function with respect to these matrices? Now, and you're going to see it gets pretty complicated pretty quickly for just this simple this simple neural network. And in fact, the way backpropagation works for like much bigger networks, where we wouldn't actually do the calculus the way we are working at. Basically, we just look at every layer, every 2 layers, and we say, okay, if we look at basically what values change over here in the second layer, how does that change kind of propagate backwards to the previous layer? And that's kind of why it's called backpropagation. But the concept is the same. How does the next, a gradient, what is a gradient? What is a derivative? We're asking, how does the function change with respect to earlier changes, right? So if we look at what changed over here, we're basically asking, what value changed to cause this change over here? That's basically what a derivative is. We're looking at kind of the relationship between changes, and that's effectively what we're doing here. So what did I say on this slide? I wrote, training the network means we're going to find the set of weights to use in our 2 weight matrices, W1 and W2, so that the network makes good predictions. We're going to do this by finding the set of weights that minimize the loss function, and to minimize the loss function, we're going to do gradient descent. Okay, now one thing to note is that gradient descent does not guarantee that it will even converge to a solution. It doesn't guarantee that it's going to find the global minimum, but gradient descent should, emphasis should, help us find some weights that do perform well. Okay, but gradient descent can get stuck in regions if it ends up being flat. And so, to combat that, you might need to try different starting locations, okay? And gradient descent also requires that we find the gradient. So here's our neural network again. 2 nodes in the input layer, 3 nodes in the hidden layer, 1 node in the output layer. And this is the goal of what we want. We want to find the 2 gradients. We want to find the gradient of the loss function with respect to our first weight matrix, and the gradient of the loss function with respect to our second weight matrix. We can think of the gradient in these cases as basically the matrix of partial derivatives. If we say, all right, our first weight matrix consists of these 6 weight W's, W11, W12, and W13, we can take the partial derivative with respect to each of those elements. Okay, so this is what we're going for, and same thing with our second weight matrix. Okay, If we had bias terms, we would also have to find the gradient of J with respect to our first bias matrix and the gradient of J with respect to our second bias matrix, okay? All right, well, let's start calculating the gradient of the loss function with respect to the second weight matrix, okay? So just because the second weight matrix is closer to the output right here, okay? So we'll work backwards and we'll find the second gradient with respect to the second weight matrix first, and then we'll find it with respect to the first weight matrix, okay? So this is where we are headed. So here is, we're gonna say, okay, what is the derivative of J with respect to W2? So our loss function is basically the difference between the actual values minus predicted values. We're going to square those things, sum them up, okay? So the derivative of a sum is also the sum of the derivatives. So I'll bring that in here. And we say, okay, well, how does this change with respect to W2? All right, well, we have a power here. So the squared is going to come down, cancel out this 1/2, okay? And then we say, so we have this, and then we have to look at this, and then there's a chain rule, okay? Because, so the actual value, y sub n, doesn't change when we change, make changes to W2, but our predictions, y hats do, and that's preceded by -1. So applying chain rule, we're going to multiply by -1. And then we have to ask, well, how does y hat change with respect to W2? So, so this is where we're going to be, okay? And then we can further split that, and we can say, well, the part, how does y hat change with respect to W2? We're going to split that to how does y hat change with respect to Zn3? So if you go back a few slides to this forward propagation, we can say, well, y hat is the result of Zn3 being inside this activation function. So we're going to say, how does y hat change with respect to Zn3? And how does Zn3 change with respect to W2? All right, how does that make sense there? Okay, let me, okay, so y hat is the result of passing Zn3 through the activation function, okay? So the derivative of y hat with respect to Zn3 is just going to be the derivative of the activation function. So if we say, well, y hat is f applied to Zn3, the derivative of this is just going to be the derivative f prime of Zn3, okay? And so if our activation function is the logistic function, 1/1 plus e to the -t, then we can do quotient rule, and we'll say, you know, f is u over v, and f prime is u prime v minus u v prime over v squared. And we'll say u is 1 and v is this, and we do all of this. And basically, we arrive at this as the derivative of the activation function. And so we'll say f prime of this is equal to this. Now, now to keep our solution easy, I'm going to just plug in f prime Zn3, knowing that f prime Zn3 is equal to this this equation right here. Okay, so so I'm just kind of plugging in the things we know. So this is where we left off. We said we have the sum of the difference between yn minus y hat times this, and now we want to know, okay, how does Zn3 change with respect to W2? So this is where we are. Okay, so if we go back to the forward propagation and we say, all right, well, what is Z? Okay, so Zn3 is just one value inside the Z matrix. So the Z matrix is n by 1, right? We have one value for each of our n observations. And we think about, okay, what do we have? We have, going into that, we have the A2 matrix is the result of, you know, that second hidden layer, or that second layer, the hidden layer. And the hidden layer has 3 columns, and we have n observations, and we're multiplying it by that weight matrix, which is 3 by 1. Okay, and so let's just focus in on one value here. Okay, and so if we have one value in the output, that is just you know, the nth value in our Z matrix. Okay, our Z3 matrix. So that's just a 1 by 1 scalar value, and that's the result of taking just one row in our A matrix, one row in our A matrix. So we're going to have A sub n, one row, 3 values in it, and we multiply those 3 values each by a value in our W2 matrix. So we, you know, you have 3 in that row, and we multiply by 3 in the column, and we multiply them and add them up together. And you know, we multiply them and add them together, and that's going to give us our single value, Z sub n here. So what is the derivative or the gradient of Z sub n with respect to W2? Okay, so if we do this, Z sub n with respect to W2, right? The result of this is going to be A sub n transpose. Okay, so you can think back to the gradient relationships from one of our earlier lectures. Where was it? I think. So if we look at our gradient relationships, we had something like X transpose W. And when you take the gradient with respect to W, you get X. Okay, but here it's not, it's A times W. And so the gradient with respect to W is going to be A transpose. Okay, because here we were assuming X is 2 by 1 and X transpose is 1 by 2. Here we have A is a 1 by 3, and so A transpose is going to be 3 by 1. Remember, we want, with respect to W is a 3 by 1 matrix, and so the gradient of Z sub n with respect to W, because W is a 3 by 1, the gradient also has to be 3 by 1. So that's why it's going to be A2 transpose here. Okay, so the gradient of this. And so that's where we are. So we say, okay, what is the gradient of J with respect to W2? And so far we have the summation of, we have, you know, we take the difference between Y and Y hat, we multiply it by F prime of Z sub n, okay? And this so far is just a single scalar value. And then we multiply that by A sub n transpose, okay? A2 sub n transpose, which is a 3 by 1. And so the result is going to be a 3 by 1 thing, okay? And we have this quantity for each observation. So you do it for the first observation, and you get a 3 by 1. Then you do it for the second observation, you get a 3 by 1. You do it for the third observation, you get a 3 by 1. And right now we're saying, okay, do this for each kind of thing, and then you sum them all up. You sum them all up, okay? Now I have to, so I'm going to do some stuff which is not pure linear algebra. We're doing some like weird wonky things, okay? So I have to preface this and say what I'm going to do next is not linear algebra in a pure sense. However, linear algebra gives us kind of a notation and a vocabulary for dealing with matrices. Okay, it gives us a notation and a vocabulary for dealing with matrices where I can use kind of linear algebra notation and multiply 2 matrices. And you will understand that that means we're going to multiply the elements in these matrices, and then we're going to add them up, okay? However, I'm also going to do certain operations that do not exist in linear algebra. Like I'm going to be doing element-wise multiplication. So I'm going to be taking, say, two columns, and so in linear algebra, you would take one column, you would have to transpose the other, or you would transpose one, and and you would multiply things out. But here I'm going to say, like, I'm going to take two columns and I'm going to multiply the first element with the first element, the second element with the second element. So that's not like a normal linear algebra thing. But by having kind of the language of linear algebra for dealing with matrices, it allows us to, simplify our results and our notations a little bit. And we can get rid of summations. Because if I were to, this is correct. This is fine as it is. And if I were to try to take this and implement it in R, perhaps, I would need to like run a for loop. And I would have to say for I, for n and 1 through whatever, or for I and 1 through whatever, do this calculation and then sum the next operation for the next observation and sum it for the next observation. And that would actually slow down our calculations. So element-wise multiplication does exist on the computer, even if it's not like a traditional linear algebra thing, okay? So what we want to try to do is we're going to use kind of the concept of matrix multiplication, and we're going to say, well, instead of having to do this summation, can I just use the entire matrix, okay? And okay, so I'm going to say, okay, if I have one observation, y sub n, I could just take the entire column of y values, the actual y values, okay? And then rather than just taking one predicted value y hat sub n, I can just take the entire column of y hat values, all right? And so y is going to be an entire column n by 1. Y hat is an entire column n by 1. And I can take the difference there, and that's fine. I'm going to get a column n by 1 of the differences between y and y hat, okay? If I think about what z is, remember z right now is just a single scalar value, and I've got n of them, one for each thing. So I can take the entire column of z values, okay? And I've got n by 1 of them. And then right now, a sub n transpose, okay, a sub n, I got one row with 3 values in it, okay, one row with 3 values in it, so it's 3 by 1. And I can say, okay, well, what if I'm sorry, I've got 3 values in one column, right, a n transpose. And if I expand that out, I'm going to get 3 rows, but now n columns. And this dimension multiplication doesn't line up. It doesn't line up. So what we want to do is we want to preserve the elements that we're multiplying, okay? But we want to be able to kind of use the matrix linear algebra matrix multiplication language or notation. And so, and again, this is not allowed in regular linear algebra. But what I'm going to do is to kind of make sure the elements are, okay, I'm going to just rearrange the terms. So this is allowed in just regular, if we think about this is a scalar and this is a scalar and this is a column, I can, with multiplication, I can move these elements around, okay? I can move these elements around and I haven't done anything wrong, right? Because if we're multiplying scalars here, the same elements are being multiplied, okay? So, so I'm going to rearrange these terms like this. I'm going to bring the an transpose here. So I've got my 3 by 1 column here. And then I've got my kind of 1 by 1 scalar of y minus y hat values. And then I've got my, the nth observation in z3, which is just a current 1 by 1 scalar. And then again, I'm going to say, all right, let's expand each of these to include all n values. And so this becomes, A2 transpose, we have our entire A matrix. And so when I transpose, I'm going to have 3 rows and columns. And then I can matrix multiply that with y minus y hat, which is n rows and 1 column. And I've got all of these z values here, okay? All of these z values, I've got n of them in a single column. And in order to kind of multiply this and this is, again, where I'm not doing pure linear algebra, but I want to be able to kind of multiply, the first, basically here I'm multiplying the nth element in y with the nth element in z. And I want to be able to do the same kind of thing. I want to multiply the first element in y, subtract off the first element in y hat, and multiply that by the first element in z. I want to take the second element in y, subtract off the second element in y hat, and multiply that by the second element in z, right? I want to line up all of these ends. So here I'm going to do what's called element-wise multiplication. So I'm going to put in this operator, this circle dot, okay? So this is just kind of a made-up operator indicating we are doing element-wise multiplication. And again, we are kind of, we're cheating a little bit, but not really. We're just trying to borrow the language of matrix multiplication along with other operations of, kind of multiplying these elements, the nth elements together with, because we're just trying to simplify our lives by saying like, okay, can I do something? Can I indicate that I want to do something that without having to like run a for loop of summations here? And that's what this is about, okay? And so so this is what we have. So we're going to say the gradient of J with respect to W2 is our A2 matrix transpose 3 by n. We're going to multiply that by this quantity, which is n by 1, which gets matrix element-wise multiplied by n by 1. And so this thing, when we do element-wise multiplication, is going to be an n by 1. The result is going to be an n by 1 column of values. And I can take the 3 by n and multiply it by an n by 1, this thing times this. And the result is going to be a 3 by 1 matrix, a 3 by 1 matrix. And you can see that by borrowing the notation from matrix multiplication and borrowing that linear algebra notation, this is going to do the same exact thing that we did here with the summation, where we take the values in here and we multiply it by kind of this first column of values here. And then, we do it for the second observation and add it. That gets handled by the matrix multiplication. We can say, all right, do this for the first column, and then do it for the second column, and do it for the third column. And I'm sorry, and they all get added up together. Okay, so we're going to do it, for every element, right? The first element, second element, third element, fourth element, all the way up to the nth element. We kind of go through and we multiply them, and then they all get added up, right? So by taking advantage of the notation that exists for matrix multiplication, they multiply and add and combine together. And so we can do this, right? And we can represent the gradient of our loss function with respect to the second weight matrix using this notation. And we no longer have a summation. We don't have to run a for loop that says do it for the first element and then run it again and add it, do it for the second element and add it, and then run it again and do it for the third element and add it, and so on and so forth. We can just use the matrix multiplication, which on the computer is much faster to do all of these kinds of things. And on the computer, there is element-wise multiplication. You can take two matrices and just put the regular old star, and that's going to do element-wise multiplication. So the computer already is set up to do element-wise multiplication, and the computer is also able to handle matrix multiplication very easily. Does that kind of make sense? Do these steps here for our gradient with respect to the second weight matrix make sense? All right, thank you for that thumbs up. I appreciate that. Let me go ahead and give you your first view quiz answer. I have too many windows open. Okay, where is it? Okay, first view quiz answer. Oh shoot, this says, where am I? I'm so sorry. 102B, week 3 Monday, lecture view quiz. This is what I want. Okay, there we go. Our first view quiz answer is the letter A. A as an apple. A as an apple is your first view quiz answer. A. week 3, Monday, 102B. Yes, okay. A is an apple. First B was answer. Okay. So let's continue on. And now we're going to find the gradient of the loss function with respect to the first weight matrix. Okay. So, so we already did it. We did it for the second weight matrix. Now we're going to do it for the first weight matrix. Okay. This first part, same as before. You know, you have y minus y hat squared, and then we do chain rule, and we say, okay, how does y change with respect to z? Does y hat change with respect to z sub n? And how does z sub n change with respect to w1? So we leave this off. This is f prime. And so we're going to say, okay, well, how does zn change with respect to the first weight matrix w1? And we split this into how does z sub n change with respect to a sub n, and how does a sub n change with respect to w1. So z sub n is the result of multiplying a sub n times our second weight matrix. Okay, so z sub n is the result of taking our nth observation, our nth row in A, and multiplying it by that second weight matrix W. And so therefore, the gradient of z sub n with respect to changes in a sub n is going to be W2 transpose. Okay, so again, this is kind of like one of so the labels are a little bit funny, but we're trying to take it with respect to A. So it's kind of like this, X transpose W, okay, except here it's not transposed. So the result is going to be W2 transpose, right? So because the result here is we need this to be a 1/3. We're taking it with respect to a sub n. A sub n is 1/3. So in order to get this to be oriented correctly, the gradient of the nth observation in Z with respect to the nth observation in A, which is 1/3, it's going to be our W2 matrix transpose, and that result will be 1/3. So we'll replace this with W2 transpose. So that's what we have here. Okay, so we're just kind of working off of this. So far we have one observation, the nth observation, and this is all a scalar value. And this thing is our first thing that's not a scalar value. It's a 1/3 matrix. Okay. And at this point, we want to say, okay, what is the gradient of the nth observation in A2 with respect to changes in W1? Well, the nth observation in A2 is the result of applying the activation function f onto the nth observation in Z. Okay, the nth observation in Z is, is a 1/3 row. It's the nth row in that Z matrix. That Z matrix has 3 columns in it. And so we're taking the nth row there. And so the derivative or the gradient with respect to this is just going to be f prime on each of these elements here. Because A, which is 1 row in our A matrix, also 3 columns, each of those things is just the result of passing z into our activation function f. So we're just going to say, okay, what is f prime? F prime of this. So this is also going to be 1/3, right? So we can already see, I can't just use traditional multiplication anymore, right? I got a 1/1 thing, I got a 1/3 thing, and a 1/3 thing here, okay? And so we're probably going to have to do some element-wise multiplication in order for our terms to line up when we do the multiplication. All right, but is this so far? Is this okay? Getting the W2 transpose and then the f prime of the nth row in Z. All right, the last part is how does Z, the nth row in Z, change with respect to our W1 matrix? So this part is probably like the weirdest, kind of the weirdest thing going on here. Okay, so we have this the nth row in our Z matrix is is one row, 3 columns. So it's a 1 by 3. And it is the result of taking your nth row in X and multiplying it by your first weight matrix W. Okay. And if we think about, okay, what are the elements that are being multiplied? Okay. The elements being multiplied is the nth row in X, that's going to be one row, and we've got 2 columns in X, right? And what is W? W is this weight matrix where we have 2 rows and 3 columns, right? So we're multiplying a 1 by 2 times a 2 by 3, and the result is we're going to get a 1 by 3 matrix. So we want to say, well, how does this resulting thing, Z sub n, the nth row in Z, change when we change elements in W, right? How does this thing change when we change elements in W, right? So so let's take a look at what's happening, because it feels a little bit strange at first. So if we look at the values in X and we multiply, and we say we're going to multiply this nth row in X by this W1 matrix, okay, we're going to get this 1 by 3 row matrix here, okay? And so we can say, all right, what if I took an element in W and I added a tiny little epsilon, okay? What if I add a tiny little epsilon to this first element? How is that going to change like the output? Okay, well, everything over here is going to remain the same. The only thing that's going to change is that if I add a little epsilon to it, that epsilon will get multiplied by X sub n1, okay, the first element in this row here, and so it would change by this. If I change the second element here by an epsilon, if I add a little epsilon, it's going to also change by X sub n1 there as well. And if I change the third element, it will also change by being multiplied by X sub n1. Same thing with the second row. Second row, if I add a tiny little epsilon to X to W21, then this kind of output will change by being multiplied by xn2 times that epsilon. If I add a little epsilon to W22, then pretty much all of the other elements remain the same, except the only one that changes is that this one is going to increase by epsilon times xn2. Okay, so the partial derivative of this Z2 or nth row in Z ends up being a 2 by 1 matrix, basically the transpose of the nth row in xn, transpose of xn. Because any change to this top row is going to be get multiplied by x of n. Any change to the second row is going to get multiplied by x of n2. So we're going to say the derivative or of Zn2 with respect to our first weight matrix W1 is going to be the nth row in X transpose. So that's going to be a 2 by 1. And so if we plug that in, we get all of these things. And again, the elements, when we try to multiply them, they don't line up. There's dimension mismatch. And so we think about, okay, what elements are being done? And again, in linear algebra, this thing where I just kind of move this and bring it to the front, this is not allowed. You cannot do this in linear algebra, okay? But we're not doing strict linear algebra here. We are borrowing the language of matrix multiplication from linear algebra to communicate that we are multiplying elements in kind of matrices or vectors together. So this kind of operation of bringing x of n transpose and suddenly moving it up to the front, not allowed in regular old linear algebra. But we're not actually trying to do linear algebra. What we're trying to do is we're trying to create a matrix that consists of these elements being multiplied together and these elements being multiplied together. And so with that in mind, if we carry out the multiplication, we can see, oh, okay, these elements are supposed to be multiplied together. We're supposed to, I have 3 elements in W2, and I've got 3 elements inside the nth row of Z, and I want to multiply, the first by the first, and the second by the second, and the third by the third. Okay, how do I do that? Well, I can use the element-wise multiplication here, right? And here I want to, I want to produce a matrix that's 2 by 3 in the end of the day. And if I take this, which is going to result in a 1 by 3, okay, I can multiply it by, the first row in X, and then I'm going to get a 1 by 3 in the top row. And then I can multiply by the second row in X, and I'll get a 1 by 3 in the second row. And so I'll end up getting a 2 by 3. So I can do this, and the result for the nth observation in X, so far we just have, if I just do the first observation in X, I will get a 2 by 3 matrix. The first observation in X, I've got a 2 by 1 element, right? I've got 2 elements, it's 1 row in X, and I'm transposing it, so I have 2 by 1. This is a scalar. I've got the nth observation is just 1 value. The nth prediction is just 1 value, and the nth element in Z is just 1 value. So this is a scalar. W2 is a 3 by 1 matrix. I'm transposing it. It's a 1 by 3, and I'm going to do element-wise multiplication with the 3 elements in my nth row in Z. Okay, so I've got for this first observation, I'm going to get a 2 by 3 matrix. And right now I have a big summation saying that I'm going to do this for the first thing, and that results in a 2 by 3 matrix. I look at the second observation. The second observation, where n equals 2, is also going to result in a 2 by 3 matrix. And I do it for the third observation, and I get a 2 by 3 matrix. And we're going to add this 2 by 3 matrix on top of this 2 by 3 matrix on top of this 2 by 3 matrix. And we do it for all n elements. And you do this calculation and you sum them all. When you sum all of these layers of 2 by 3 element matrices on top of each other, the final result is going to be a 2 by 3 matrix. So we are just, for any one observation, we're going to carry this out. It results in a 2 by 3 matrix, and we're going to add them all across all n observations. And if you add, 100 2 by 3 matrices on top of each other, you're still going to end up with a 2 by 3 matrix at the end. And that's where we are right now. And so again, we want to ask the question, can we get rid of the summation? And instead of having to run a for loop or something, and when I do my calculations and say, do this for the first element, do this for the second observation, do this for the third observation, can I take advantage of kind of our matrix multiplication syntax and do it so all of the multiplication and all the addition is all done in one step? And the answer is yes, we can. Okay, so we're going to say, all right, take this. Right now I have a summation for each of the n observations here. What if I expand this out? Okay, so instead of just the nth row in X, what if I take the entire X matrix? What does that look like? The entire X matrix, transpose is going to be 2 by n. Remember, the end goal is we want a 2 by 3 matrix at the end. If I expand out the column Y, I get n by 1. Y hat is n by 1. I can matrix multiply that by expanding out all the elements in Z, which is going to be n by 1. W2 is 1 by 3. There's no subscript n here, so it's not suddenly going to get bigger when we look at it for all the elements. It's still going to be 1 by 3. And then what about this Z sub n? So the Z matrix has 3 columns, and now we have n rows, not just 1 row. And so this is going to become n by 3. So I'm writing all of the subscripts here, and so we can say, okay, well, what does this thing look like? Okay, well, if we do element-wise multiplication here, this is going to remain n by 1, and I can multiply this by W2 transpose, and that's 1 by 3. And this actually all multiplies together. This is a 2 by n. This is going to be n by 3, And if I can element, we'll multiply that by this, which is n by 3, and I get a 2 by n times an n by 3. And that will be end up multiplying out to be a 2 by 3. Okay, so this is 2 by n by 1, 1 by 3 times that. This is n by 3. This times this element will multiply. I've got n rows, 3 columns. I also have n rows and 3 columns. I can element multiply each of those things. And when I multiply that all together, I get a 2 by n times an n by 3, and the result is going to be a 2 by 3. And that's exactly what I want, because the W1 matrix is a 2 by 3 matrix, and so the gradient of J with respect to W1 needs to be a 2 by 3 matrix. And so this produces the result that we want. So that could also be used as a guiding principle, as you say, well, you know, I want to calculate the gradient with respect to W1. W1 is a 2 by 3 matrix, so I know the gradient has to be a 2 by 3 matrix as well. This is a lot. This is a lot. I hope these notes, I don't imagine everything was like crystal clear all up front, and so you're probably going to have to review this just to kind of make sure you understand each of the steps. And I hope my notes are clear enough. It took a long time to typeset everything and put all of the subscripts underneath each element. So, but I'm hoping that it is clear and it makes sense. So take the time to kind of go through this. Let me go ahead and give you your second Vieuxtemps answer. Second Vieuxtemps answer today is the letter D. D as in dog. D as in dog is your second Vieuxtemps answer, D. All right, so this is what we're going to do. We're going to go ahead and turn it into code, and we'll run the neural network. And, you know, turning things into code feel a little intimidating, but what I'm hoping to show you is that all of this stuff that we turn into code is directly as just a straight translation from the math into code. So first we're going to write a function for activation function. The function here, I wrote function of t, and the output of this is going to be 1 plus e to the negative t, and that's all I have. Function z, I'm going to have 1 divided by 1 plus e to the negative z. That's our sigmoid activation function. Okay, so that's straight up. We have our input data matrix for x and y. Input matrix is 3 rows, 2 columns. Is 3 by 2, and so you know, 3, 5, 5, 1, 10, 2, and then the output in y is 75, 82, 93. These are just from our kind of silly example from the very beginning, I think, from last. This is from last week's notes, and so this, I'm just taking these things, right? So this was my silly example. And they said we're going to take this 3, 5, 5, 1, 10, 2, 75, 82, 93. And we're just throwing that into here. Okay, and to kind of get this to work, we're going to scale our values so that they are in between 0 and 1. And one reason for why I'm scaling the values is because if you look at the sigmoid function, my sigmoid function? Okay, so here's the sigmoid function. So one thing is that the sigmoid function, there is slope between, say, like -2 and +2. But then once your x values or your t's get higher than 5 or lower than -5, the slope there is pretty much 0, right? And so that can be a problem when we're doing gradient descent. When we are doing gradient descent and our slope is 0 or very close to 0, then the gradient will say this is the direction we're going, but the step size we're going to take is very small, right? Because when it's, again, if you're rolling a ball down a hill, when this hill is steep, the ball's going to roll fast. But if the hill is very, very like close to being flat, it might not be perfectly flat, but it's very close to being flat, the ball's going to roll very, very slowly. Okay, so so we don't want to have X values that are like 10 or 5, because at X equal to 10, the slope is almost 0. So we're going to scale it so they're on values between 0 and 1. It doesn't have to be between 0 and 1. We could have scaled it to something else. But here I'm going to just say, all right, let's just divide everything by 10. So the biggest value is 1, and the smallest value is going to be, somewhere between 0 and 1. Similar thing over there. Over here for our y, we just divide everything by 100. And again, that's going to put everything on a range between 0 and 1. With the sigmoid function, that's probably a decent range to have it. Okay. We're going to have our input layer has 2 elements in it. Our hidden layer has 3 elements, and our output layer has 1. And I just put these in as variable names. This is our forward feed, and so we're just going to carry this out. We're going to say, here I'm going to just start off with arbitrary matrices, W1 and W2. W1 is a 2 by 3 matrix, and W2 is a 3 by 1 matrix. I'm just filling them out with arbitrary values of 1 in the beginning. So we're just going to have 1, 1, 1, 1, 1, 1 for W1, and then W2 is just 1, 1, 1, 3 rows, 1 column. And we'll do forward feed by doing X times W1. I'm just taking this, right? X times W1 gives me Z2. And then we apply the sigmoid function to Z2 to get A2. And then we're going to do A2 times W2 to get Z3, A2 times W2 to get Z3. And we apply the sigmoid function on Z3 to get Y hat. So this is just doing forward feed, taking our math and turning it into instructions in our code, where this, this percent star percent is the matrix multiplication operator. The cost function, this is our J. This is the difference between the actual values and the predicted values. So I have Y minus Y hat. We're going to square that difference. We're going to sum it up. And then I'm multiplying it by 0.5 because that's what we had in our thing. And so right now my cost is 0.0153. Derivative of this sigmoid function. This was from an earlier slide, but it's e to the negative z divided by 1 plus e to the negative z quantity squared. That's from right here, e to the negative z, 1 plus e to the negative z quantity squared. That's what we have there. All right, and the gradients, we went through all of the math, and we said the gradient of J with respect to W2 is A2 transpose minus Y times negative Y minus Y hat dotted with F prime Z3, or not, element Y's multiply. So I'm called this quantity delta 3, and then this is going to be A2 transpose delta 3. So delta 3 is negative Y minus Y hat times sigmoid prime Z3, and then the gradient itself, dj dw2, is A2 transpose times delta 3, matrix multiply. So this is the element-wise multiplication, which is not a normal linear algebra operation, but we can do it in the computer. This will take the elements and do element-wise multiplication, and then we do matrix multiplication between A2 transpose and delta 3. Similarly, we do something for the gradient to the first weight matrix. We say the gradient of J with respect to W1, dj dw1, is X transpose times this thing. This whole thing is delta 3 times W2 transpose, element wise with F prime Z2. So delta 2 is going to be delta 3 multiplied by W2 transpose, element wise with F prime of Z2, sigmoid prime Z2. And that's delta 2. And then I do X transpose times delta 2, X transpose times delta 2. So we're just translating directly from the math into code for R. And we're going to do gradient descent. We'll do gradient descent. So here, I'm going to populate just random values in my W1 matrix and random values in my W2 matrix. And I'm going to create a matrix to keep track of the loss function, the cost. And what we want to see is that the cost function decreases with every step as we conduct gradient descent. Okay, so this is the gradient descent algorithm. Okay, so what is happening? First, we take our current values of W1 and W2, and we do forward feed to get my y hat values. And once I have my y hat values, I'm going to calculate the difference between y and y hat, and that's going to be the cost function. So I just do forward feed. X times W1 gives me Z2. Sigmoid on Z2 gives me A2. A2 times W2 gives me Z3. Sigmoid on Z3 gives me y hat. So I do forward feed to get my y hat values, and I calculate what's the difference between y and y hat. Now that I have y hat, I can calculate my gradients. So inside my gradient formulas, I need to calculate, I need y hat to calculate those gradients. So we're going to get delta 3, negative y minus y hat times sigmoid prime Z3 gives me delta 3, and dj dw2 is A2 transpose times delta 3. And then I take delta 3 multiplied by W2 transpose times sigmoid prime, and dj dw1 is going to be X transpose times delta 2. So this gives me my gradients based on my current weights. And then the gradient descent part is take your current weight values, W1, and you're going to subtract off some scalar multiplied by your gradient. So you just do W1 minus scalar times dj dw1, and that's going to give you the updated W1 value. You take your current W2 value and you subtract off scalar times dj dw2 to get your updated W2 value. And once that finishes, we will repeat the whole process. Okay, and here I said do a loop of 10,000 iterations. 10,000 iterations. So we're going to do 10,000 steps of gradient descent. Every single time we take our current values to get our y hats, our predicted values, and because we need those predicted values to get our gradients. And so now that I have my predicted values, I can calculate what my gradients are. And then now that I have my gradients, we're going to take our current value and take a small step based off of our gradient. Okay. Right now I have my scalar value set to 5, and that seems to be an okay step size here. All right, is that okay? Gradient descent, seeing this gradient descent here. All right, okay. Thank you for that feedback there. And now this is the result, okay? It says, okay, after 10,000 iterations of this thing, these are the coefficients we have for W1 and the coefficients for W2. And I have no idea what these coefficients mean. So that is one of the downsides of neural networks is you get these coefficients, you get these weights at the end of the day, but you're unable to do, they're not interpretable. We don't know what this coefficient does. We don't really know what this particular node means. But that doesn't really matter. That's not the point. Okay, we can see, all right, how after we trained our network, what kind of predictions are we getting? So these are the predictions it's making. It's predicting 0.7499998, 0.8200548, 0.9298944. The actual values are 0.75, 0.82, and 0.93. And so we can see our predicted values are quite close to the true values. We're probably overfitting them, considering that we only have 3 observations and we have 9 parameters to mess around with. We probably overfit our values. But anyway, this is what we have. This is what the cost function looks like. So in the beginning, we had rapid improvement in the cost function. The gradient descent rapidly improved, and then we hit kind of this flattish region, and we were stuck there for a little while until we hit around the 2000th iteration. At the 2000th iteration, we saw some improvement, and then maybe around the 4000th iteration, we kind of hit a flat area, and not gaining much improvement after that. This is the log of the cost history, and so we can see, rapid improvement in the beginning, again, flat region, but we let it run for a long time. 2,000 iterations, finally it hit something, there was a breakthrough, and then after that we're getting kind of improvement. It's I guess incremental improvement. And so even though it kind of flattens out here, I guess this is like, you know, it's like every step you're getting halfway closer to the end, but it's just every single time it's getting smaller and smaller and smaller. So that's what a simple neural network looks like. I want to show you using the neural network on in a case that I think is kind of neat. So we are going to look at the MNIST handwritten digits data set. And this is kind of like, you know, one of the earlier applications, but also one of the kind of a very important application of applying a neural network in, and basically it's like one of our early image recognition applications of a neural network. And so let me just MNIST data set. Have you guys heard? Who here has heard of the MNIST data set? Anybody? Okay, so the MNIST data set is kind of this kind of almost what about the IRIS data set? Have you guys heard of the IRIS data set? Okay, so the IRIS data set and the MNIST data set are these very classical, very important data sets, at least far as machine learning, and they're kind of like almost like canonized. All right, and so the MNIST data set, let me show you pictures. This is basically what it looks like here. Let me zoom in. So one of the earliest kind of applications was for, you know, sorting mail. All right, so you're at the you know, you write an address on an envelope and you put it in, and then the post office receives it. And for a while, you know, handwritten letters had to be sorted by hand. There would be a human who would look at the letter and they would read it and they'd say, okay, zip code, you know, 90210, that's Beverly Hills. And they would put it over into this side and they say, okay, zip code over here, it's going to New York or whatever. And a human would have to do this. And they said, well, can we speed this up with computers and things like that? And so, so some person, probably a grad student or something, they scanned a whole bunch of text. They scanned all of these envelopes and their zip codes. And because they knew they saw the city name, they knew what the zip code should be. So they knew what the zip codes were supposed to be. And they scanned them and they cropped them all kind of perfectly. So all of these images are these 28 pixel by 28 pixel things. And sometimes you see them, you know, kind of reversed colors. But basically you have these 28 by 28 pixel images for these different, for every single digit. And so this is what it scanned. And then they entered, you know, this is supposed to be a 5. This is what they scanned, the 28 by 28 pixels. This is supposed to be a 1. This is 28 by 28 pixels. This is supposed to be a 9. And they have 70,000 of these images, okay? 60,000 in the training data set, and then 10,000 in the test data set. And so you can download the data. I think I put this on Brew and Learn. So if you go to Brew and Learn, you can download the data sets, I think. Download the MNIST data. And so you can download these, it's these ubyte.gz files, unfortunately. And if, so you're gonna download these, and then if you're on Mac, you'll have to open up Terminal, navigate to the folder where you downloaded the file, and then you'll call gunzip, gunzip, I should say, gunzip, and then you'll type in train-images-idx3-ubyte.gz, and it will g-unzip that. And you have to do this 4 times, one each for the training images, the training labels, the test images, and the test labels. Okay. If you're on a PC, Windows machine, you'll download these 4 .gz files, and then you'll have to download and install 7-zip. 7-zip is a free zip file utility, and it is able to unzip the .gz files. Okay, so I've already done that on my computer. Where is it? Okay, so I've downloaded these, and so the 4 files are inside. So here I've got my script downloaded, and inside this same folder I have another folder called MNIST, and so these are the zipped GZ files. Okay, and then basically using 7-zip, I extracted them. Okay, so I extracted them, and so these are the IDX ubyte files. All right, and this is what we use for the data here. Okay, but again, the data are these little 28 by 28 pixel images representing each of these things representing data. Okay, there's a script here that's going to take that data and we'll load it in. Okay, and then here's a little function that will take the image and arrange it into something that we can see. So let me so I'm going to go ahead and load the MNIST data, and then we can take a look at, say, one of these images here. Okay, and so here's that first image actually from the data set. Okay, so on my computer it shows up the ink is in black. Over here the ink is in white and the background is black, but it's just one is kind of the opposite of the other. And we can say, okay, well, what if I wanted to look at the second image? Okay, so here's the second image in the data set. Okay, and then the third image in the data set looks like that. Okay, and then say like the 5th image in the data set is the number 9. Okay, and they're all kind of stored. They're all stored in this matrix, and I happen to have just the perfect width on my screen where I have 28 rows going across. Okay, and so you can actually see where it's zeros. Okay, basically there's no ink, and then where it's dark, you can actually see where those numbers are. Okay, but if I happen to change the size of my thing, you wanted to look at the matrix, it looks all wonky like this. But let me try to go back and get the right. I have this wrong. Okay, so now it's kind of the right width there. But anyway, so that's what we have, and you can take a look at the image here. I want to play a little video from 3 Blue 1 Brown that that covers this. Let me pause my recording. Okay, I'm going to pause my recording just so I don't get a copyright strike on YouTube, because I'm going to upload this video to YouTube, and so if you play someone else's content and stuff, you get a copyright strike. So basically, if you're watching the video, you'll have to go to this 3 Blue 1 Brown neural network video. I'll give you the timestamp. I don't remember the exact timestamp off the top of my head, but I'll find it and I'll mention it after I unpause the recording. So let me pause the recording. So what that video illustrates is that we have basically 28 by 28, a total of 784 neurons here, and they get arranged so that all 784, I'm going to just show this very brief clip where all 784 are basically just stretched out into just one vector of length 784, and that's going to form our first our first layer in the neural network. Okay, and that's all we're doing here. And then in the 3 blue 1 brown video, he has 2 hidden layers, but we're just going to have 1 hidden layer. That's just an arbitrary choice. So I'm going to just have 1 hidden layer. And then, but we do need 10 neurons in the output layer. Okay, we're going to have 10 neurons in the output layer, 1 neuron corresponding to 0 and 1 neuron corresponding to 9. Okay, basically 1 for every possible digit. There's 10 digits, 0 through 9. And one thing is that even though the output is a number, this is actually a classification problem. It's a classification problem. It's not a regression problem. We are trying to take the inputs here. Okay, we have 784 values that corresponds to pixels in an image, but the computer doesn't know. It's just 784 values. And based on the 784 values here, we're trying to predict, is this a digit a 9? Is this a digit a 4? Is this digit a 0? And we're trying to do that. And we're trying to classify that. And the reason we want 10 nodes and not 1 is that if we have 1 node, this is going to be a regression problem. And you might think, well, why can't we just say, okay, predict a 0 or predict a 2 or 3 or 4 or 5 or 9 or something like that with a regression thing. The problem with regression is the way we measure error in a regression problem is difference between the actual value and the predicted value. So let's say the actual value was the number 9. Okay. In a regression problem, if we predict the number 8, we say, well, you didn't get it right, but you did a pretty good job. If we guessed the number 4, that's wrong, and the number 0 is like very wrong, right? In regression, how far you are off makes a difference. And so if the true value is a 9, we're going to say 8 is a better job than 1. Okay. And that makes sense if you're trying to predict, like, how much money did we earn? If we truly earned $9, then predicting that we're going to make $8 is a better guess than predicting if we made $1. Okay. But that doesn't work for digit classification. If the true number is a 9, guessing the number 8 is just as wrong as guessing the number 1. Okay, they are equally wrong as far as digit classification goes, right? If you're trying to dial a number, okay, it doesn't matter if you are off by 1 digit or 6 values, okay? If the true number is a 9 and you punched in the number 1 or you punched in the number 8, it's not like dialing the 8 is going to get you any more closer to the real number, okay? So for digit classification, the actual value and the predicted value have to either be the same or they're wrong, okay? Guessing an 8 when the true value is a 9 is just as wrong as guessing a 1. So we can't use 1 node, we need 10 nodes. So anyway, so the way we're going to do this is we have 10 nodes, and the correct value will be a 1 for the 9 and 0 for everything else. And we're going to try to train it so that the output is going to give us a value close to 1 over here and close to 0 for everything else. So what I have to do is I have to take the true answer of, say, 9, and we are going to turn them into like zeros and ones, okay? So if the true answer, in this case, this is, the true answer is a 9, we need a 0 for the nodes 0 through 8, okay? So I've got 10 nodes, 1 for each digit. Basically, the first column is for 0, the second column is for 1, and the 10th column is for the digit 9. And so this corresponds, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1 corresponds to the digit 9. And then this one, 0, 0, 0, 0, 0, 1 here, and 0, 0, 0, 0 corresponds to the digit 5. So, and again, the very first image was a 5. Okay, so that's what we want. So we're gonna we want to turn all of our values into a bunch of zeros and ones. Okay, and And then we're going to go ahead and run the code that we have for our neural network. So our sigmoid function, we have, this is all the same code from earlier. Okay, so sigmoid prime, the cost function. And here, my input layer, I have 784 nodes. My output layer is going to have 10 nodes. And my hidden layer, arbitrarily chosen, I'm going to have 30 nodes in the hidden layer. Okay. Let me just show just like a little diagram here. So again, the idea here is I've got, this image, 28 by 28 pixels. This is 784 values. So I'm going to have 784 nodes. My neural network has all of these connections going to 30 nodes in the hidden layer, and then we're going to have 10 nodes in the output layer. And what we're hoping to get for a good guess is we're hoping to get values that are close to zero. So something like 0.001, 0.001, 0.001, 0.001 for all the nodes. And then we're hoping to get something like 0.99 for the node that corresponds to 5, and then zeros everywhere else. That's what we want. Okay. We're going to do something called batch gradient descent, just so that our computer doesn't choke. Because I've got 60,000 images in my training data set. And so what I'm going to do is I'm going to just select 10 images at random. All right. And then we're going to calculate the gradient using those 10 rows. And then we're going to take a step in that direction, in the direction that the gradient descent tells us to do. And that's going to help our computer, because doing the matrix operation with 60,000 rows is going to require, basically require a lot of computational power from my computer. And so that's just like, just a few too many matrix multiplication operations to ask the computer. So we're going to just split this up and make it easier and just say, hey, do 10 rows. And then we're going to take the 60,000 image data set and split it into 6,000 batches of 10. Okay, we're going to shuffle them up, do 6,000 batches of 10, and say we're going to do gradient descent doing that. Okay, so let me zoom in a little bit here. Okay, so my code, I'm going to run set up my matrix. Okay, and I'm going to, for my first weight matrix, I'm going to do 784 by 30, and I'm going to just generate a bunch of random values between negative 0.5 and 0.5. So I'm going to do RUnif. RUnif generates values from 0 to 1, and I'm going to just offset that by negative 0.5. So now it's generating values from negative 0.5 to positive 0.5. And I'm going to populate my W1 matrix with that. And then I'm going to do the same thing for my W2 matrix. I've got 30 values in my hidden layer, and I've got 10 in my output layer. And so W2, so we can see W1, 784 rows, 30 columns, W2, 30 rows, 10 columns. And they're just filled with kind of random values here. So actually, let me just run this, okay? Okay, and then we're gonna do batch gradient descent. So I'm going to say, all right, take our thing, split it into batches of size 10, and then split them out. And then for each thing, right now our values in our input matrix X are values from 0 to 255. And so what I want to do is I'm going to just scale those. I'm going to divide everything by 255. So I just kind of want you to look at this, but this is the exact same code that I had in our notes. Okay, so first, basically, I'm going to just take the rows in my batch. Okay, I'm going to scale them down so that they're on a scale from 0 to 1, And then we do forward feed to get our current y-hat predictions. We use our current y-hat predictions to calculate our gradients, dj dw2 and dj dw1. And once I have my gradients, I do gradient descent. I take my current weight matrix and I subtract off a scalar times the gradient. I take my second weight matrix, subtract off the scalar times the gradient, right? And so that's the code. This is just doing matrix multiplication and doing gradient descent. So I'm going to go ahead and run this. This will take a few seconds to run. So it's running, working through 6,000 batches of 10, and now it's done, okay? And now we can test our performance, and we can see how well our neural network operated, okay? So here I'm going to go ahead and take our test set, okay? And in our test set, we have a whole bunch of things. And what I'm going to do is I'm going to take our test set and use the weight matrices that we have. Okay, so we use gradient descent and we arrived at some values for W1 and W2. And I'm going to do forward feed. I'm going to take our test set, our inputs, and we're going to pass them through with our weight matrices. And we're going to say, okay, go ahead and make columns or make guesses based on these things. So we do sigmoid function. And so right now my y-hat matrix, like if I look at, say, the first row, right, I have a bunch of these things, okay? So let me just round it to, say, 3 decimal places, or let's say 6 or 5 decimal places. Okay, and so this seems like it worked out well. We have 0, 0, something very close to 0, right? 0.00005, 0.00000, 0.00001, and then we have one thing at 0.9995. So this corresponds to digit 7. Okay, so the first digit, when you look at this, we're hoping it should be a 7. Okay, so basically I said, give me which column in here is the maximum, and that here's the 8th column, and then this corresponds to digit 7. So we're going to do so the guess here is going to be a 7, and we can say, okay, well, what does this digit look like? Okay, and indeed, when we say show me the digit here, the digit is a 7. Okay, all right. What about the second column, or the second entry? So the second entry in our test data set. Okay, our results are not as good. Okay, we have 0.00371, 0.0006, 0.69143. So not quite as extreme as 0.99995, but 0.69. So that's the maximum value. All other values are also close to 0. This one came out to be 0.00158. So we're going to guess it's a 2. Okay. And then for the number for 6 and the number for 0 came out not quite, we're also small, but a little bit bigger than the others. Okay, but the number for 2 came out the largest. So let's go ahead and take a look at that digit, and indeed that's a digit 2. Okay, let's take a look at, say, the third row. The third row, we have corresponding, I would say, to a 1. Okay, 0.99982. That's for column 1, and we did look at that. Indeed, that's a column 1. Okay, the fourth row, the guess is a 4. Okay, and again, if I look at the fourth row, we can see, yeah, indeed, the node for digit 0 is the highest, and if we look at that, indeed, it's a 0. Okay, so what we can do is, so far, I mean, as far as these 4 observations go, our neural network is working. And I'm hoping, I'm hoping you feel like, oh, I understand a little bit what's happening here. We're just really doing these matrix multiplications and multiplying stuff together. There was no like mystery here. I didn't use some mystery package that did stuff. We're just doing operations that we can kind of follow. Okay. And so what I can do is I can do a comparison between the actual values and what our neural network guessed, okay? And this is the result, okay? So if the actual value is a 0, we guessed 0 962 times. There were a couple times where we guessed a 2, a couple times where we guessed a 4, a couple times where we guessed a 5, a 7, a 6, 7, 8, 9, 8, or 8, okay? When the actual value was a 1, we guessed a 1 1,113 times. We made some mistakes. When the actual value was a 2, sometimes we made a few mistakes and guessed it was a 0, but most of the time we guessed a 2, okay? Some mistakes. So basically values along the diagonal we got correctly. These are some mistakes. When the true value was a 9, we guessed the number 4 64 times. And we can kind of understand that, right? The number 9, when you handwrite it, can look like the number 4. So we can kind of understand that kind of mistake. And so we can just kind of look at the diagonal and see, all right, how often were we correct? And we got around 93% accuracy, 0.9287. So not perfect, but also considering how simple our neural network was, this is, in my opinion, this is not very bad, right? This is, we're successfully classifying what these digits are, 93% of the time. And, if we take a look at some of these mistakes, we can say, all right, what were these are all of the different mistakes. We can say, okay, when did the neural network misclassify a digit? And it said, okay, it made a mistake on the 9th observation. All right, so let's go ahead and take a look at what the 9th observation was. Okay, so it says the answer is that it should be a 5. Let's take a look at what this digit looks like. And what did our neural network guess? Our neural network guessed a 6. Okay, and when we look at this, we go, oh, neural network, I'm not mad at you. All right, this person had bad handwriting, so neural network, you guessed a 6. The true answer was a 5. Yeah, the true answer is a 5, but neural network, I'm not very mad at you. I understand how you can make a mistake like this. Okay. All right, over here it says it got the number 78 wrong. Observation 78. Okay, the true answer is a 2. Okay, neural network, you probably should have gotten that. Neural network guessed a 7. Okay, so I'm not quite sure what happened, but yeah, that one's clearly a 2. But sometimes, you look at some of these things, the true answer is a 9, and it guessed a 4. Okay, and we go, okay, I can kind of understand how the neural network is guessing wrong on some of these things. But overall, I think it's kind of neat, and again, we can look at some of these observations, see, what it was. So the true answer is an 8. Yep. And it guessed a 6. And we go, okay. Yeah, not quite, we can understand that this should be an 8 as a human, but also like the handwriting's not great either. So I think, we feel a little bit like forgiving the neural network a little bit here. But overall, we're getting, in my opinion, pretty decent results. And again, this was just a very simple neural network where, we just did matrix multiplications, one hidden layer with 30 nodes in it, and then we just did a gradient descent. Okay. And that's actually that's all I have for today. I just wanted to kind of show gradient descent and the neural network for the MNIST training data set. And in your your next homework assignment, you'll work with a neural network. And the hard part of the homework assignment is going to be calculating the gradients with respect to the bias matrices. So my hope is the notes I provided here, covering the steps regarding calculating the gradients for each of these things. My hope is that you can use kind of the steps that I've done here to figure out what the gradients should be when you take the gradients with respect to the bias matrices B1 and B2. Okay. All right, we'll go ahead and wrap it up here today. How many view quiz answers have I given you so far? 2. Okay, the last 2 answers are both the letter B. Okay, the last 2 answers are both the letter B. B and B. B as in bear. B as in bear are the last few view quiz answers for today. Okay, we will go ahead and end here for today. Have a great rest of your day. I will have office hours later on. Otherwise, we will see you on Wednesday for the midterm exam in class. All right, good luck, and we'll see you then.